Thank you, Marina. Thank you, everyone, for coming. Again, it's a great pleasure. I've learned a lot this past week, and it was nice to see old friends and meet new people. Okay, so the second lecture, I'll try not to go too long, because I know we have lunch. But the first lecture we saw some Higgs bundles that I kind of went really quickly on. But today we'll do a construction for minimal surfaces where there will be something that resembles a Higgs bundle, but it's not exactly. So I'll point that out when we get there. And in Franz's lecture, we kind of saw that there are these two signs in the non-compact symmetric space setting versus the compact symmetric space setting. And in the first lecture, we dealt with the non-compact symmetric space. I'll just remind you, this was SO3R on SO3, and today, so this was yesterday, and today the symmetric space we'll be dealing with is CP2, so that's SU3, 2 or something like this. So this is CP2. Okay, so this is compact today. So, okay, so I should mention this is what I'll be talking about is joint work with Sebastian Heller, Franz Pedit, and the paper should appear in the archive maybe at end of next month or so, but it will appear soon. So, okay, good. So a little bit of maybe motivation for, of course, I defined some of these words. I mean, minimal surface, we all know, but maybe Lagrangians might be new for some people. So kind of the motivation, and this takes us kind of far from minimal surface theory, but nevertheless, it's kind of the underlying motivation for some of this work. So it really comes from string theory, where it is purported that space-time is 10-dimensional. So here I have 4 dimensions, your space 3 and the time 1, but then you have these 6 hidden dimensions. And this is in the form of a Calabi-Yau threefold. Okay, so it's not super important what a Calabi-Yau threefold is, but at least let me define this. So it's a complex 3-manifold, so real 6 dimensions. It'll be Kähler, and it'll be a Ricci flat. It emits a Ricci flat metric. And there's several inequivalent definitions of a Calabi-Yau. The one I will take is a little bit stronger, but nevertheless, it's a standard definition. In particular, there exists a nowhere vanishing holomorphic 3 form called omega, and this is usually called the volume form, the holomorphic volume form. Okay, so some definitions will just say that the first Chern class is 0, but this here is a little bit stronger. So okay, so that's the our working definition of Calabi-Yau threefold. And so this thing in string theory led to the following SYZ conjecture. So this is the Strominger, Zaslow, and I'll just kind of draw a picture because I don't, the emphasis of this talk is not on the SYZ conjecture or Calabi-Yau threefolds, but kind of the picture is that if I have a Calabi-Yau threefold, the cartoon picture one might expect. Now, there's some adjectives that, I'm not a string theorist. I don't work in mirror symmetry or Calabi-Yau threefolds, but kind of the cartoon picture one expects is that I have some real 3-dimensional base. So here's a real 3-dimensional manifold as my base. I have a singularity locus, which in some cases is expected to be codimension 2 in a trivalent graph. So let me just draw this here as a singular locus. And off the singular locus, I have this nice vibration by a special Lagrangian retori. So draw this cartoon picture here. So here's a nice point P away from this singular locus. I have a vibration by special Lagrangian retori. Okay, so that's a lot of words. So I ought to define these words. So I'll start with kind of the easiest part. So by 3 torus, I actually mean the 3 torus. So this is, let me say T3 is S1 cross S1 cross S1. Okay, so you can see that the dimensions add up. Real dimension 3 in the fiber, real dimension 3 in the base. Complex 3-dimensional manifold, real 6-dimensional. Okay, Lagrangian, well, remember I have this Kähler form, so I have a symplectic form. So the Kähler form, which I'll denote omega, restricted to this T3 is identically 0. Okay, so that's the condition. And I'll remind you that Lagrangian you need, for a symplectic manifold, which is even dimensional, Lagrangians are half dimensional. So I do need that this is a real 3-dimensional object. But if I take a half-dimensional submanifold, restrict the symplectic form to this submanifold, it's identically 0, then it's Lagrangian. So probably most people know these two words. This last word is kind of maybe not super well known to perhaps this audience, but the last adjective special modifies Lagrangian. And here, notice that we have this holomorphic volume form, so I'm going to use this. So it means that we want that the imaginary part of this holomorphic volume form that restricted to my 3 torus, that I want this to be 0. Another way to say this is that it's calibrated by the real part of this holomorphic volume form, which I don't discuss, but for those who know calibrations, this is another way to describe special. Okay, so this is kind of the SYZ conjectures, the conjectures that you should be able to find this vibration. Maybe you have to do some what are called instanton corrections or go to a large complex structure limit. But okay, so that's just a cartoon picture. But that's the motivation for our talk today, because what one might be interested in is point singularities from, of the Calabi-Yau. So you could see that this is a smooth vibration away from the singular locus. But you could try to imagine what happens when you get closer and closer to this red singular locus. You could start to degenerate. And one way one might degenerate, as we kind of saw in yesterday's lecture, but in a different flavor, so I could think about pinching a generator. So here's my a picture of a 3 torus, right? So I mean, it looks like a 2 torus, but the cross sections, it's S1 cross S1 cross S1. You can kind of rope off one of the copies of S1 cross S1. So I can imagine maybe the cross sections here are 2 tori, right? But if I start to pinch this generator, you could see that this looks more and more like the following. So I could kind of put something like this. And again, I still have this cross section here is a 2 torus. And if I kind of zoom in, the picture I get is the following. This is a cone whose link is a torus, so it's a cone whose link is a 2 torus. Okay, and of course, this is still sitting inside C3. And in fact, this is still a special Lagrangian cone. Okay, so kind of the point singularities, one particular model of these would be special Lagrangian cones in C3 whose link is a torus. Okay, so these are, and when I have such a cone in C3, well, C3, you could think of this as R6. I could take a unit sphere, that's S5. So I could intersect with the 5 sphere. So here's my picture. That's 5. And maybe you take 1 copy. Then I have this torus sitting inside S5. And now, an important thing that I should have mentioned about special, I mean, since we have that it's calibrated by Harvey and Lawson, you know that it's actually a minimal cone. So in particular, when I project to S5, it's actually a minimal surface. So, but usually people say it's a special. So because its lift is this special Lagrangian cone, but instead, S5 is 5-dimensional, so I can't say Lagrangian. But it turns out that the correct property is that it's Legendrian. So I don't get too much into this, but S5 has a natural contact structure. And you could think of it as a maximally non-integrable 4-plane field, and the surfaces, maximal dimension submanifolds, which are integrable along this contact structure. Those are called Legendrian. Okay, so it's an analog of Lagrangian for symplectic manifolds. Okay, but the special part is important because this implies minimal. Okay? And more or less, if you're minimal, then you're special if you do some if you go back to this holomorphic volume form and you rotate it. Yes, Parker. No, well, there's this whole rich industry of constructing these cones, but the techniques are, yeah, some of them are algebraic in nature, but there is some sort of description about kind of the moduli space of these tori that you can get. Okay, good. Okay, so now I have a minimal surface inside S5. And now what I can do is I can take the Hopf projection to CP2. So my cartoon picture of CP2 looks very much like S5. And well, I mean, you could think about, I mean, this is given by the Hopf projection. I mean, how do I go from CP2 to S5, right? The fibers over each point in CP2 is a copy of S1. And so I could project, and what I get is also a torus. And now the objects that are here, I mean, this is a Ramanujan submersion. And so in fact, this is also a minimal surface. But now the Legendrian condition gives us that it's actually Lagrangian. And these are the minimal Lagrangians in CP2. Okay, so you should be a little careful, especially if you haven't seen these two words together. These are minimal surfaces. So I'll write this down just because it's important enough. So these are minimal surfaces which, in addition, are Lagrangian. So it's an extra factor. So it's not that I'm restricting to a smaller class of surfaces where I vary the area. So I really do minimal surfaces. I find a minimal surface, and then I hope that it's Lagrangian in addition. So these are, and we'll see that in the case of CP2, when we do the setup, it's not too hard to come up with examples of minimal surfaces, and it's not too hard to come up with examples of Lagrangians. But getting both at once is not so easy. So in short, it's actually possible to go backwards. If you start with a minimal Lagrangian surface in CP2, you could take a lift, and you'll land up in S5, and you get a special Legendrian surface, and then you could just cone S5 to get C3, and then you get your special Lagrangian cone. And there's no genus restriction here. The only thing that happens is that here, you might have to pass through a threefold cover to go from CP2 to S5, a threefold cover of the surface, which of course for genus 1 doesn't matter. You still get a genus 1 surface, but for higher genus examples, you might have to, the genus might go up. But we'll see this threefold cover when we do the setup. So in short, you can go back and forth. So if you're after just special Lagrangian cones in C3, then you can work in one of these other two spaces if you please. Okay? So in terms of kind of the history, well, I mean, there's a couple natural examples. I mean, kind of, the simplest example of a minimal Lagrangian surface in CP2 is, well, RP2. RP2, sitting inside here is certainly a minimal surface and a certain Lagrangian. You can check that. When you lift up here, you get an equatorial two-sphere. So that's no surprise. The two-sphere in S5 is minimal and Legendrian. Okay, so you can go back and forth. The other examples that one sees for CP2 is well, you can have the Clifford torus. The Clifford torus is a genus 1 example in these lift. But for a while, I mean, these were kind of the only known examples, and people have studied extensively the case of genus 1, and many examples were constructed. So let me just kind of write down a few of the names. So genus 1 been well studied. So there's Sharapov has some examples. Ma rediscovered them. Carberry and McIntosh have many examples, and etc. So this is a whole industry of constructing them, and kind of the question Parker alluded to is that there's kind of integral systems machinery to construct these tori that Franz kind of explained at the kind of the tail end of his lecture. So genus 1 is fairly well understood. In contrast, for higher genus, there are almost no known examples. There's exactly one paper in the closed case of higher genus through the Haskins and Capelleas. Let me just kind of highlight the year. 2008, I believe this one was published. So there they come up with the first examples of these higher genus minimal Lagrangian surfaces in CP2, and they do it for all odd examples. So, okay, so G is odd. And they have one example where G is 4, but it's an ad hoc construction. But aside from this, no other examples have been constructed. And let me just kind of quickly sketch how they do this. I mean, this is hard analysis, but at least let me tell you the setup. So here, I mean, remember, it doesn't matter which space you work in. They work in S5. Okay, so kind of the construction we talk about today will be in CP2, and you'll see why this is kind of a nicer space to work with when we do this, interval systems, loop group methods. They work in S5, and what they do is the cartoon picture. I mean, you can really see that you can see the very clear division of labor. So Haskins in his thesis comes up with these special Legendrian cones, and so if we're working in S5, so here's S5, as I said, kind of the simplest example of a special Legendrian surface is the two-sphere. So you take an equatorial two-sphere, which maybe I don't draw S5 anymore, so I just draw a two-sphere. I take a copy of a two-sphere, and Haskins in his thesis has these examples of these special Legendrian cylinders. And what you do is you glue these cylinders, at antipodal points. Okay, so and you have some k-fold symmetry. So here you have another. So of course, I'm not very good at drawing. So you can imagine where I'm drawing these x's, you glue one part of the cylinder and you glue the other part of the cylinder. So of course you have, S2 is special Legendrian. These cylinders are special Legendrian. You glue them together. But of course, when you glue them together, the solution, I mean, the combined object is not necessarily minimal Legendrian. So then, Capelleas, I mean, this is the famous Capelleas gluing method. Then you have to perturb and fix it so that you get a solution. So there's a lot of hard analysis. But you can see the building blocks. You start with S2, you start with these cylinders, you glue, and then you fix the whole thing, and then out comes a new example of a special Legendrian higher genus surface. So that's kind of the thing. One thing you could, and maybe I should say why it doesn't work in even genus. There's symmetries that they choose. If you want even genus, you end up trying to glue two cylinders at the same location. But because of this, they can't do even genus examples. And one thing that you'll notice with their construction is that this, and this will be relevant later in the story, is that the area growth, their examples, grows linearly with the genus. Why? Because my two-sphere has some fixed area, and I'm just adding on handles of these cylinders. So each time I add a handle, I pick up a genus, I pick up a fixed amount of area. So that's kind of yes. Yeah. Oh, there they use a different symmetry. So it's a tetrahedral. So you can imagine two tetrahedron and the glue cylinders there. So there's a different symmetry. So here, this is a cyclic symmetry. There you use a tetrahedron. So, and it doesn't work for the other Platonic solids. So that's one of the shells. Okay, so that's kind of the brief overview of what was known. And so the new result is the following. As I said, well, it should be 25 to appear on the archive. So let's see. This minimal Lagrangian surfaces. In CP2 of genus G is equal to K minus 1, K minus 2 divided by 2, or K large. So let me just pause here. So you see this formula, and if you're bored, you could see that there are even G's that you can get. So if you take K to be 1 mod 2 or sorry, 1 mod 4 or 2 mod 4, then you see that G is even. Okay? And there's also odd examples, of course. K has to be large. Now you see this number, you think triangle numbers, you think the Fermat curves, and you're exactly right. So whose conformal structure is matches the Fermat curves. We talked about, fortunately, we talked about Teichmuller space last lecture, so now you know what Riemann surfaces are. We can look at the conformal structure on these minimal Lagrangians, and they match with the Fermat curves. Now I'll define the Fermat curves shortly. So okay, or I could just write it now here. You could think of these as curves in CP2 that satisfy the following equation: x to the k plus y to the k plus z to the k is equal to 0. So these are what the Fermat curves are. Okay, and then the last thing about these minimal Lagranges is that, moreover, their special Legendrian lifts to S5 are embedded. So for topological reasons, you can never get a minimal Lagrangian surface, a higher genus minimal Lagrangian surface in CP2, which is embedded. There's a topological argument that shows you that you necessarily have to have, I believe it's 2G minus 2 points of intersection, but these come with signs. So you can never hope for embeddedness in CP2, but when you lift, you have a hope, because you can think about what happens when you lift from CP2 to S5. You have these points that are coming together, but when they lift, you have this S1 fiber over a single point. So if you're lucky, then these points of intersection all split and they no longer intersect upstairs. So it is possible. And in our construction, by the way, we actually do find 2G minus 2, exactly 2G minus 2 points of intersection down in CP2 that we can find. But the problem is with intersection, there's a sign associated to it. So there might be other points where you have plus minus signs of intersection that contribute, that overall cancel each other out, but maybe they're there. But we think these are the only ones. So anyway, so they lift to embedded surfaces in S5. And I asked Capital Ace, I think a couple of years ago, whether they know their examples are embedded, because they work in S5, and he says that he thinks they're only immersed. So they're certainly immersed, but I don't think they're embedded in S5. So these are the first known embedded examples in S5. So that's kind of the statement of the result. Okay, so now let's do setup then to kind of describe this construction. Okay, so we work with CP2. So I'm not assuming too much background for this talk. So I start with CP2. I can think of these as complex lines through the origin in C3. Okay. Now, if I just start with the surface S, let's say it's a smooth surface, I don't impose any conditions on S so far. No Riemann surface structure, no topology, just a smooth surface. Maybe make it oriented. But okay, so then if I look at a map F from S to CP2, I guess let's make it an immersion. Smooth immersion. Then there's a little bit of yoga that we do first here. So you'll notice that with CP2, there's what's called the tautological line subbundle. You see, because again, using this perspective of CP2, what happens, what is CP2? It's the collection of these complex lines through the origin in C3. So if I take a point in CP2, this is precisely a specific complex line through the origin in C3. So sticking that line on CP2, I get a line bundle. Okay? Not only a line bundle, it's a line sub-bundle, because there's a fixed C3 once and for all. I mean, it's exactly what Franz was, in analogy, it's to the spectral curve that we saw in Franz's previous lecture. I mean, that was defined tautologically. So here we have a subbundle of the trivial C3 bundle. And my trivial C3 bundle, I'll just put a underline under the C to denote that it's a trivial bundle. Okay, so this is a tautological line subbundle of C3 over CP2. So now let's think about what a map is. Well, you take a point on the surface, and this gets sent to, well, a point on CP2. That's exactly what a map is, right? But what is a point on CP2? That's, as we saw, a complex line through the origin in C3. So via pullback, then what I have is that I have I can pull back the tautological line subbundle. Now I have a line subbundle of the trivial C3 bundle over S. So kind of the first step in this yoga is that I can go freely from maps between a surface to CP2 and line subbundles of the trivial C3 bundle. So that's kind of the first step. Okay. Now the next thing I'll do is, so now we just add more and more conditions. So I still have a smooth surface. So the next thing I do is following. Okay, so now let's upgrade our surface. So not just a smooth surface, let's choose a Riemann surface structures. And maybe not to have to come up with new letters, I'll use S is now a Riemann surface, so I don't use X. So I guess I used X for my Claw-Biao, and maybe there's a capital X here with the projective coordinates. Okay, so now it's a Riemann surface, and now we saw from Franz's lecture and other people have mentioned Mike's lecture as well that harmonic maps are conformal invariant. They're invariant. They only depend upon the conformal structure for the domain. Okay, so that's why we choose a Riemann surface, because we're marching towards minimal surfaces. So at the very least, we need a harmonic map. So now let's say that this is a harmonic map. Okay, and again, it only depends only on the conformal structure. Okay, now remember I have this immersion, so I can take the derivative and split according to type. So I could split according to type. So this will be a 1-0 part, and this will be a 0-1 part. And you can see where, maybe I'll write this out once. So this is a section on S of hum, which takes me from, so to have, I don't want to be too sloppy. So instead of writing this L or the pullback, let me denote this as standard L here. Okay, so this takes me from, well, the derivative is going to take me from L to L per. So I have a Hermitian metric on C3. I have a line. When I take the derivative, then it lands me in the perpendicular plane. And of course, this is tensored with K. Likewise, this del bar here, you can see that it's similarly L to L per, and now I have a K bar here. Okay. Now we saw that harmonicity, we have a Laplacian associated to this, and you see you have a del F here. So harmonicity of the map tells us that del F is holomorphic. And likewise, del bar F is anti-holomorphic. Now, if our main mission is to construct minimal Lagrangians, then I could safely conclude that I don't want. Okay, so I know that this is holomorphic, but what's the problem? The zero map is holomorphic, right? I mean, if this is zero, that's certainly holomorphic, and we want to exclude this. Why? Because if this is identically zero, let me just write this, then this means that F is anti-holomorphic. Okay, and likewise, the same argument here. If del bar of F is zero, then identically zero, then that means F is holomorphic. But holomorphic and anti-holomorphic completely opposite from Lagrangian. Because if you remember from your first lecture of complex variables, holomorphic, the J operator preserves the tangent plane. And this is rotation counterclockwise by 90 degrees. And if you recall from symplectic geometry, well, the Lagrangian condition is going to take you from the tangent plane to the normal plane. So clearly these two are incompatible. And in the literature, if you look back old enough, kind of the term they use for Lagrangian is totally real. Okay, so this tells you that holomorphic and Lagrangian are not compatible. So here, since we're looking for both minimal and Lagrangian, then we could at least safely exclude the case where this is identically zero. Okay. So now since del F is holomorphic, then this means, and it's not identically zero, this implies the zeros of del are isolated. And likewise, the same argument here tells you that the zeros of del bar of F are isolated, which means that del F, remember I wrote down the tensor type here, you have Hom from L to L perp. But now that you know that the image here has isolated zeros, this in fact the image lands you inside a line subbundle. So this lands in a line subbundle of the trivial C3 bundle, call it L plus. And likewise, del bar of F lands you inside another line subbundle, L minus. And here, remember, this is a subbundle of the perp space. Okay, so now I have a pair. So L plus is orthogonal to L, and L minus is orthogonal to L. Okay, so that comes from the condition that the map is harmonic and not holomorphic or anti-holomorphic. Good, okay, so we're getting closer, right? Because now I have a harmonic map, but what else do I need? I have that it's harmonic and that it's an immersion. So if I want an immersed minimal surface, then I need conformality, as we've seen. Now we have conformality. And as we've seen in both Mike's and Franz's lecture, well, there's a holomorphic object associated to harmonic maps known as the Hopf differential. And you could write this in terms of, in this case, the pairing of the Hermitian metric with these two line bundles. But another way to write it is that if I have a metric, which I never specified on CP2, without writing too many words, I guess I could safely use maybe H as the Fubini-Studi metric on CP2. What I could do is I could take the metric, I could pull it back. So I don't think we saw this interpretation in either of their lectures. So you could pull back the metric. And since I have a Riemann surface, it makes sense to decompose by type. I could take the 2-0 part. And this will be a holomorphic quadratic differential. So my Riemann surface, unfortunately, was S. And then now I have the canonical bundle squared. Okay, so this is a holomorphic object. But what this means in terms of L and L plus is that the conformal condition means that L plus and L minus are orthogonal. Okay. And now since L is orthogonal to these two, now I have a splitting of the C3 bundle then. Let me go to this end. So putting this together, we have a splitting, an orthogonal splitting of the trivial C3 bundle into the following. So here, once again, here's C3. Now let me put L in the middle, L plus, L minus. Okay, so I haven't, so here all I've used so far is that it's a conformal harmonic immersion. Okay? And I used Lagrangian to preclude that it's a holomorphic, anti-holomorphic map, but I haven't used exactly the characterization of Lagrangian. So now the Lagrangian condition then, together with the immersion condition, will actually tell you that L minus is identified with K inverse L, and L plus is identified with KL. So maybe I don't spend too much time to describe this, but you could work out, so the immersion condition will tell you that the the derivative never vanishes. And the Lagrangian condition together with conformality will tell you that the norm of this is equal to the norm of this. So the point is that these isolated zeros cannot vanish simultaneously. Okay, so in fact, so this means that you actually get a bundle isomorphism, and if you work it out, then this is the correct bundle isomorphism. So that means, in fact, this trivial C3, and now it's just isomorphic, gives you this bundle here. Now, you could twist everything by L inverse. So without loss of generality, you can actually assume L is the trivial line bundle. And doing this gives you a rank 3 bundle, which I will also just write as C3. Just be a little sloppy here. But what I get at the end is the following bundle here. And if you remember from yesterday, this bundle appeared in my Higgs bundle for SL3R Hitchin representation. So so it appears once again here in this setting. So all I've done here is this is splitting here. And this trivial bundle, which played the role of L, this is the position vector. If you remember the position, this was what gave us the map F that we were originally seeking. So we're almost there. So we have a bundle. And now let's, in fact, it's a holomorphic vector bundle. And now what we're looking for is something that looks like a Higgs field, but not a Higgs field. Okay, so now we take the standard flat connection, standard unitary flat connection on C3. Okay. And the thing I didn't get to talk about yesterday is that when you construct a Higgs it's not good, but that's fine. Okay, so then, right, so then we could split this up. So then what remains, since this diagonal part is this unitary, then what remains has to be unitary, and what we get is the following here. And this adjoint is with respect to the Hermitian metric on C3. And then you could see that actually this phi that one gets is the following one form. And here you have a Q. I think actually, I see it. Okay, so I think I messed up already because I flipped. So this is, okay, let's see. Yesterday, I think I had, okay, I mean, it doesn't matter where you put the K minus 1 or the K, right? You clearly flip it. I think in my notes here, I actually have this. So let me just make that change now. And then what I get here is this 1, 0, and 0. Okay. And this is a holomorphic section of NV tensor K. Okay, so here I have a holomorphic rank 3 vector bundle, and I have something that has the correct tensor type of the Higgs field. So you might say this is a Higgs bundle, but of course, it depends on your definition of a Higgs bundle. Strictly speaking, yes, this is a holomorphic vector bundle together with the Higgs field, but it does not satisfy the correct Hitchin equations that we saw in yesterday's lecture, both in mine and Franz's. Namely, it has the wrong sign because we're in a compact symmetric space. And you can see part of the sign issue comes from how we split the connection. Here, these signs are different from when if you were to do it with Higgs bundles. If you were to do it with Higgs bundles, then you would actually have a plus sign for the adjoint here. Okay, so yes. Right. Okay, so the reason why I say it's not a Higgs bundle is because in order to get back your flat connection, you don't use the self-duality equation, the Hitchin self-duality equation. It is a Higgs bundle. Okay. Strictly speaking, yes, I know. Okay, so this maybe I had without in scare quotes, but so, sort of philosophically, then this does not fall under not abelian Hodge. So okay, so yeah, so you could technically say, yes, it's a Higgs bundle, but I think that's a little bit misleading. So okay, but this is just a philosophy. I mean, I don't think there's, okay, so, oh yes, sorry. Yeah, so I mean, it's technically just isomorphic, right? And originally it was on the nose. I mean, this is actually sitting inside C3, but the problem is I make this isomorphism, then okay, yeah, but thank you, that's good. Okay, so if I write the zero curvature equations, we saw this in Franz's lecture, then we get that the flatness is equal to this here. And then I have that this phi is actually holomorphic. Okay. And in kind of in coordinates, I guess, or kind of more down-to-earth statement is the following. So I could choose once again, choose sigma to be a conformal background metric on S, then my equation looks like this. And here, I could spend a little bit of time to just kind of highlight the differences in the sign. Q, remember Q is a capital Q here. So here, Q is a holomorphic cubic differential. And then I have the usual curvature term. So you'll notice that compared to yesterday's lecture and also with Mike's lecture with the Bachner equation, these are exactly the two wrong signs. I flipped the sign. Okay. Now, as an exercise, I don't have time to do this, but if you had the nice signs, let me just kind of write this back out. If you're bored with the nice sign, Mike showed us for the Bachner equation, he had this nice PDE theory of sub and super solution to prove that you have a solution. But it's not hard to show that you also have a unique solution. And this is, I could, a unique solution, you should think these are the coefficients, right? So you could see that the only thing that is that you need to be prescribed is this Q, right? I mean, this is already fixed, right? Because I choose my conformal background metric to be a closed surface. So in this case, let's say that S is a closed surface, higher genus, because that's what we're after. So here, you might as well choose the hyperbolic metric. So now this term becomes a -2. Now, if you want to do a maximum principal argument, you assume that there's two solutions for a fixed Q, and you subtract them. And if you subtract them, you see that this term cancels, and then you could group these terms and factor it accordingly because you have the same Q. And then you know that for a smooth function on a closed surface, it attains its maximum somewhere or its minimum. And then the Laplacian, depending on the correct Laplacian, will be either non-positive or non-negative. It doesn't matter. And then you derive a contradiction because the two solutions you have, let's say U1 and U2, there'll be a difference somewhere. Okay, so and that gives you a contradiction. So if you're bored, this is a very easy exercise, and it works with these two signs. Okay? Now, and then if you don't believe me, you could try to run that exact same argument with these two signs, and you find out that everything falls apart. You don't get desired contradiction. Now, another thing you could do, which is a little sneaky, is that, well, you could say, well, the sign here is bad, but I can get rid of it if I choose Q to be 0. And you could try, but what you'll find out is that let me erase this. If you set Q to be 0, this goes away, right? But what do you see now? 2 curvature of the conformal metric, this is a -2, right? On a higher genus surface. If you choose Q to be 0, this term goes away. But now, and U is just some function, so you see that this is negative. It's completely negative on the right-hand side. Now you're in trouble as well, because you can never find such a solution. Okay, so what this is saying is that in higher genus, when this Q is exactly 0, you don't get a solution. Whereas in kind of this case, if you were to choose Q to be 0, you could find that there's a solution. In fact, you could easily see that U is equal to 0 is a solution. And that tells you that the Bloch-Q metric that we saw in last lecture is exactly the hyperbolic metric, because the conformal factor is 1. Okay, so that's just a kind of a cipher mark. And there's different sign variations, right? So in Pedit's talk, they studied the minimal Lagrangians in CH2, and the sign combination is as follows. So this here is this, and then it's this here. Okay, so and then the last sign combination are these elliptic affine spheres, where it's a minus here and a plus here. Okay, so, and in this case here, let me just write this out: elliptic affine sphere. It's a similar computation that in higher genus, even if you choose Q is equal to 0, you can never guarantee a solution. Okay, and these have been worked out, in these other sign variations. Solutions have been constructed, sometimes through direct methods. So I should mention there's a paper by Lofted, and Zaslow, where they do find solutions for the elliptic affine sphere equation on the thrice punctured sphere, but this requires some hard work. Okay? And we saw in Pradeep's talk that they find solutions here in the punctured case, but in the closed case, Lofton and McIntosh have studied this. And then in the original sign case, then this goes back to take Wong's equation, and then many people have studied this equation. So that's just kind of a note of the sign variations. But okay, so this is the zero curvature equation. This is what you need to solve in order to guarantee that what you get is a minimal Lagrangian, because you could trace this construction backwards. If I start with this flat connection here, satisfying those equations, then I get the splitting of the trivial C3 bundle into these three lines of bundles, and the middle L is exactly the map that I'm looking for. So one way to kind of think about this, and again, this is some philosophy, there's two ways I can think about a surface sitting inside CP2, let's say. Either I take this abstract surface and I stick this inside CP2, right? That's certainly one way to do it as an immersion. Or I start with this abstract surface and I build CP2 around me, or I build C3 around me. And that's this latter perspective where you have your fixed Riemann surface and you're constructing this line bundle decomposition to recover C3. So that's just one last piece of yoga there. Okay, so that was set up. Now let's, okay, so at the end of the day, we want some flat connection, and we want, kind of the loop of flat connections that we saw in Franz's talk. I used Nabla here. You see, I have this flat connection here. I could add the spectral parameters that we saw. So that's, and then here, and you want some symmetry properties. So in particular, let me just write this out, but you want that it's unitary for lambda on the unit circle, okay? And otherwise it's a flat SL3C for lambda in C star. You want it to be trivial for lambda is equal to 1, right? Because when lambda is equal to 1, exactly that's the standard unitary flat connection I had on C3. And then I need two more pieces of symmetry. So there's a threefold symmetry, which I don't write explicitly, but you can see there's some symmetry between these three line bundles, because you see these three are pairwise orthogonal. So if I do this harmonic maps, del takes me to L plus, del bar takes me to L minus. If I were to continue by taking del, I land back in this L minus. So it's this three cyclic symmetry that we have here. And then there's, so this is what gives us minimality. And then there's a twofold symmetry. And this encodes the Lagrangian condition, because you could see that when we saw Lagrangian, that this told us that this bundle is dual to this bundle. So that was the Lagrangian condition. Okay, so you seek some sort of flat connection, loop of flat connection satisfying these properties, and that's quite a bit to ask in the case of higher genus. So exactly what Franz had mentioned, then what we do is that you start with a Riemann surface, and you want to exploit symmetries to quotient it down to something manageable, namely the thrice punctual sphere. Okay, so now we can actually go to our choice of Riemann surface. So let's look at the Fermat curve then. So this is just x to the k plus y to the k plus z to the k is equal to 0. So you can see these are homogeneous coordinates living inside CP2. Okay, so this here, 0 set lives inside CP2. Now, one thing that you'll notice is that this is holomorphic, right? This is holomorphic inside CP2. So there's a little bit of confusion I should try to preempt. Namely, the minimal Lagrangians that we construct is not given by this algebraic formula, right? Because remember, this is holomorphic, and the Lagrange is completely, it's opposite to holomorphic. However, this equation here has a Riemann surface structure, so it's just easiest to write this sitting inside CP2, but it carries an intrinsic conformal structure, and that's the conformal structure that we use. But as a model, it's often nicer to write this equation so you can see it living inside CP2. So our surfaces also live inside CP2, but it's not this equation. So I should mention this. Okay. But since this Fermat curve using this model is holomorphic, it's automatically minimal. So you could see that if you just want examples of minimal surfaces inside CP2, it's not that hard. You just write polynomials like this, and then you have that it's minimal. Okay? And Lagrangian is not too bad either. You have to do a little bit of work, but there's like a tubular neighborhood theorem due to Weinstein that says once you have a Lagrangian, you could kind of deform and still get Lagrangian surfaces. So there's plenty. Another way to do it is once you have a Lagrangian surface, you hit CP2 by symplectomorphisms that are not isometries, and this will just generate more and more Lagrangians. Okay? But to do both at once is not easy. Okay? So that's what we start with, this Fermat curve. And you can see that the genus of this Fermat curve is exactly k minus 1, k minus 2, divided by 2. Now I forget, let's see, try to do a computation here. So I maybe genus, let's see, when k is 4, genus 3. Okay, so here's an example when k is equal to 4. Okay, so now you have some obvious automorphisms of the Fermat curve, and as I said, it's helpful to look at this model. Notice there's an order k automorphism where I just multiply x by a k through to unity. I have one that multiplies y by k through to unity. I also have one where I multiply z by k through to unity. I can also cyclically permute these three variables. The point is that if I exploit these symmetries, these automorphisms, I can quotient my Riemann surface, and you could do this elementary Riemann-Hurwitz computation, and what you get in the quotient is a thrice punctured sphere. So this is CP1 minus 3 points, and as Franz mentioned, you could, these 3 points are flexible. You could send them anywhere you want, so you might as well choose 0, 1, and infinity. Okay, so this is now thing we have, and this cover determines a representation, because if I go, or at least a representation, because I know that if I go, some number of times around this loop, this will correspond to going some number of deck transformations on this surface here, and I can figure out exactly what order I need to guarantee that the loop closes. And I think this is like an order k, and order 3, if I'm not mistaken. I don't tell you which exactly are the points. But now what you do is you find a nice, see, the symmetric space we're working with is SU3. So I want to find a nice finite subgroup of SU3. And already this, there were many instances where this differed from kind of the non-abelian Hodge Higgs bundle theory. We saw a sign change. We saw a different way to split the connection. But another way that we saw, as Franz alluded, is that the representations are entirely different. For SL3R, Hitcher representations, we saw that these were, well, at least when SL2R even, these were injective, discrete and faithful representations, right? So here, we're not dealing with injective representations, far from it, because we want the surface to close up. Whereas if you remember from the hyperbolic affine spheres, these are equivariant. They never close up. They look like the hyperboloid. So they never close up. So here we're looking for finite subgroups. Why? Because we want the surface to close up. If you go around some number of times downstairs here, you want this to eventually close up upstairs. And if it never closes up, then you just have something that's equivariant. So that's why you choose a finite subgroup. And using this cover, you can write an explicit representation, rho, which takes me from the fundamental group. Let me give this surface a name, M, into SU3. Okay? So you choose this finite subgroup correctly so that when you go around k many times here, you close up. When you go around three times here, it closes up, and likewise when you go k times, it closes up. And I should point out here that the fundamental group is the free group on two generators. So this, of course, is not finite. So again, emphasizing that this representation is not injective. So you do this. Okay, then the last step then is, of course, I'm suppressing a lot of things, but now you have a chance, because if you try to, do this loop group method on a higher genus surface, you would have two G generators. You would have one relation that you needed to satisfy, namely the product of the commutators is trivial, and that's a lot to ask for, especially if you start with holomorphic data. Then you have to make sure that you close for all these generators and you satisfy this relation. Here, you've made the problem a lot simpler by taking this the quotient by these symmetries. You have essentially two generators. Okay, so kind of the last step is that you use this very nice thesis to the Lawton, who has explicitly described the SL3C character variety on the thrice punctured sphere. So let me write M here, okay, via trace coordinates. So, I mean, this is mimicking kind of the situation in SL2R where if you take enough traces, trace squared, then you nail down the actual representation. Whereas in a higher rank, it's not so easy, but his thesis shows that if you're on the triply punctured sphere, then enough trace coordinates, or about 9 of them, will nail down the representation. Okay? So in our case, you could actually prove a similar result explicitly, and it brings it down to 3 trace coordinates. But the point is that now you can apply this loop group method and DPW, where you find a nice potential that's modeled on this thrice punctured sphere. So something of the form some residue at 0 and 1. And the point is that now you can compute the monodromy using this, what's called a Fuchsian potential, because it has simple poles in the space parameter. It doesn't necessarily have simple poles in the lambda parameter, but you can later gauge it. But this is okay, because as a starting point, you can use this to find the correct representation that guarantees that your surface closes up. So there's actually 2 steps, because the first thing you need to do is make sure that the representation you get, which a priori lives in SL3C, is unitarizable. So here you could use the Lawton result, an implicit function theorem argument, to guarantee that the representation you have actually lands inside SU3 or up to conjugation. I mean, trace coordinates are invariant under conjugation, so everything is up to conjugation. So that's where we use the character variety as opposed to the representation variety. But then you can guarantee that the monodromy lives in SU3, and then you could use the implicit function theorem argument again to make sure that it matches exactly on the nose to this representation they have. So this guarantees that the surface closes. So then if you choose this potential correctly, then you can use an implicit function theorem argument to guarantee that you have that the surface closes up. And this is why you see that you have large K in the theorem here, because 1 over the genus, or K, will appear in this potential here, will involve these functions, and you have to, the implicit function theorem only guarantees, you need to take a small enough interval. So you go from 0 to epsilon, where it's 1 over the genus, and you to 4. And then once you do this, then you get these examples of minimal Lagrangian surfaces. Let me just say in the remaining 2 minutes, one last thing about kind of what these surfaces look like in the limit. Because when we saw the Hassens capillaries, there's a very nice way to think about them in that you have the 2-sphere and you're gluing on minimal Legendrian cylinders. Here, the way I presented it, yes, we have this differential geometry set up, as you can think of it, as a sort of Higgs bundle, and then a loop of flat connections with some properties. You have symmetries here, but you might say, well, what does the actual surface look like when it's sitting inside CP2? In this case, now we lift to S5, and kind of the data we get from the potential tells us that in the limit, it kind of looks like this. So let me kind of draw this picture. There are 3 circles of symmetry, which you can kind of already see from the Fermat curves. So you could see that you have a kth root of unity coming from this factor of x, you have a kth root of unity coming from y, and you have a kth root of unity worth of points on z. So you have these 3 circles on which you have k points spaced equidistantly on the circle. And each one of these points, you can compute near it that in the limit, what we get are these spherical caps. So these are spherical caps. So this is an S5 picture. So these are circles. So let me write S1. And then these are spherical caps. So these are parts of pieces of S2. Okay, so you have these parts of S2, and they meet. There's some combinatorics to it. I've maybe drawn myself into a corner here, but they meet. So let me draw this big enough, and then here you have another one, and they meet. So not all of them, but some you can arrange. You can figure out which one of these caps meet the other two at this point here. And in the limit, you could see that you have the singular point here. Okay? But if you blow this surface up at this point here, you could find that the tangent space is actually the image of the tangent space is embedded. It's actually a Shirk type surface. So then you could run kind of standard analysis argument to show that the surface you have is embedded, because near here it's embedded, and you know how the actual surface deviates from this model. Only deviates up to second order, and you can control the first order growth to be arbitrarily small. But otherwise, you have these spherical caps, and then away from these spherical caps, they meet at Shirk surfaces. So that's kind of the limiting geometry. Surface, which is not too surprising, because pieces of S2 certainly are special Legendre. So maybe that was a bit quick, but here's a good stop. So I'll stop here. Thanks so much for your attention.
So who has questions?
So I got a bit lost there. Where is the dependence on K eventually?
The dependence on K. Okay. Well, so right here, I mean, this depends on K here. The order of the. Then, of course, then you need to choose a potential so that it generates the correct monodromy, right? So the potential you pick better have monodromy that matches up with the desired representation here. So the representation I picked, of course, I'm being sloppy, also has to depend on K as well, right?
So
they depend on K as well. I've kind of suppressed it. I mean, it's a family of flat connections, right? So maybe I should. Right. So there, yeah. So I should, yeah.
It's very large. This guy.
Yes, exactly. Depending where, or a point, depending. Yeah, but. Yeah, for the recording,
Oh, for the recording, sorry. Yeah, for large K, you have also solved unitary stability problem and everything because you know the surface. And then you apply the implicit function argument around that limiting K. So, but better to think of 1 over K than for, 1 over K is the parameter. So if you add 0, you have a sphere, you have unitary stability, and then you do implicit function argument that you are nearby, you still have unitary stability and so on. And then that generates then small 1 over K, which means large genus.
Charles, thanks for a beautiful talk. This Q you chose, is it up to you to choose, or
Pardon?
the Q?
The Q, yes, the cubic differential.
Yeah, is it up to you to choose, or is it unique?
Oh, no, it's not unique, because actually for every so for a Q we can actually construct 2 different surfaces that have the same Q. So that's kind of cheating, because you have these spherical caps, right? But then you have kind of the other part of the cap, right? I mean,
okay.
So then you could do that. But that one will not be embedded in S5. So of course
Okay.
you can see, right? If I have a small patch here, then I have the rest of it. So
But is it true that if you have a minimal Lagrangian, is it unique, or?
No. So I just gave you an example there for a single Q, you can construct at least 2.
At least 2,
yeah,
exactly.
Right, and then I doubt there'll be any uniqueness, because I mean, you try to do a maximum principal argument, it doesn't work. I mean, of course, it's not a proof, but So maybe you can ask for embedded ones, so maybe that's I'm not sure, right? Because you could say that, right? I mean, if you're asking for embedded ones in S5, maybe for a particular Q it's unique, but because the example I gave you was not embedded, but this I don't know because I mean, yes, yes, right.
If Q were DC cubed on C or some torus, every minimal Lagrangian torus has DC cube. So this equation has an infinite dimensional solution space even on a torus, right? So fixed Q, you know. Yeah. So I think your question was something like that. If you fix Q, do you have in genus 1? Certainly not. And I don't believe also in higher genus you could. It's a bit more tricky there, but in general you have more solution. Yeah, finiteness, right? I would think so. Yeah.
Well, not countable because for the Hassen-Caplets they have countable already for a fixed genus.
Different Hopf differential.
Sorry, no, Hopf differential. Oh, never mind.
Different cubic differential.
Yep. Yeah.
I think finiteness is probably.
That probably is.
Okay, if I may, I have a small question. You mentioned the number of intersection points in the beginning, but aren't these things zero homology? How do you find how can you find the number of intersection points?
You're asking about the points.
Right, the points. Yeah, at the beginning you said we know they're not embedded.
Let's see. Okay, yes. Right. Let's see. Let me see if I could remember now. Right. Let's see.
We can talk after.
But right. I mean, there was a way that we could explicitly find. Yeah. But maybe now I don't. Yeah.
Okay. Other questions? Okay, then. Oh.
Okay. So in here you have so some time ago you have mentioned that for large enough genus there will be some minimal Lagrangian surfaces in CP2 which will be, I mean, whose conformal structure would match the Fermat curve. So do we have estimates on the size of that K?
Yes, that's a good question, right? So we use this model for all K, but of course our surfaces, since it's an implicit function argument, then as Franz clarified, it's 1 over K is the parameter we use. An implicit function argument only guarantees you for small enough epsilon, right? But in principle, I mean, the proof of the implicit function theorem is somewhat explicit. You could actually trace through the analysis to try to get as sharp of a bound as possible. So in other settings, Sebastian Heller, Martin Trezet, they've done something similar on the 4 times punctured sphere, where they're actually able to compute, get really good bounds using the implicit function theorem. And I think at one point they had something like, in the millions, and I think they got it down to like 4 or something. So it is possible to, if you carefully trace through the analysis, to try to decrease that number. And right, I should mention, conjecturally, we believe that this family, this K goes all the way down to, well, 3. So that is to say, maybe even okay. So I mean, there's a natural family. So genus 0, it's the round sphere, and then genus 1 is the Clifford torus, and then so on. So that's a fairly natural family. So we think it should all go all the way down there. So but that's
okay.
Yeah. Good question.
Let's thank Charles again.